introduction. Okay, hello everybody.
No.
It's so nice to see you here finally in person. Okay, I'm looking forward to see all the other guys also. So that they get here as soon as possible and as safe as possible. So today we start the second module of statistical physics. It's going to be statistical physics with little Python so far.
Yes, so
Not so much Python, but Jean will tell you more about the concepts that are overarching statistical physics and integrating it with broader concepts like information theory. And so you have the almost unique opportunity to interact with the teacher. So take advantage of this as much as you can. And also, I don't know if they can hear me from
it'd be nice to
remotely.
If the others, do you hear us?
If you hear us, please write in the chat that you can hear us well. Oh, yes. Thank you, Anna.
Okay.
Great. So you can chat. Great. Hi, Idris. You can chat. You can interact with try to speak. Let's see if we can hear you.
If we can speak?
Oh, yeah. Okay, you can also speak.
Yes, we can.
If you have questions, okay? Good.
Okay.
Well, it's working even better than I expected. All right. So enjoy these first lectures, and we'll be around, okay?
All right. Welcome. So this is the second part of this course that you started with Roman. Roman took an approach which is a more, let's say, this is the usual approach of introducing statistical mechanics and the way it has been discovered, okay, thanks to in particular Boltzmann. What I will try to do during this module is to take a slightly different approach, which is more based on, let's say, a more modern understanding of the concepts behind statistical mechanics, in particular information theory. So have you ever heard about information theory? Do you have an idea of what it is? Or a guess, maybe from the name? You can guess, huh? So what could that be? It's the theory of what information is, okay? So one of the, I will write through information theory. So one of the most basic concepts that we have a kind of vague feeling of what it means without really knowing what it means until we dive into this field is what is information, okay? And one of the great understanding of Claude Shannon, who is the father of information theory, was to provide a clean definition of what it is, okay? And Shannon called this object, which is a way to quantify and to define what information is, entropy, okay? And this is not for no reason, because Shannon understood directly from the beginning that it was a concept very connected to the entropy in statistical mechanics. Okay, so the name is there really to recall us that deeply there in the concepts there is a close connection with statistical mechanics. Okay, and in this course I would like to dive a bit in this connection. Okay, so to take this more information theoretic view of statistical mechanics. Okay. All right. So I don't know if I think you've seen from the mail, I wrote quite detailed notes. Okay, so I advise you to have a look at this during the course. I think there is essentially everything that I will say is in there, probably even more detailed than what I will do. So in this course, I will focus on the chapter 1, 2, and 3. And the 4, which is on communication, I will not do it. I will not cover it. Okay? So what I will do today is first to recall something that you already did a bit with Roman, but repeating is always good. I will recall some basic definitions of discrete probabilities, okay, so that we're on the same page. And when I say a random variable or an ensemble and things like this, we have a common definition, okay? All right. So we'll call that basics, or okay, sorry, I need to get used discrete probability. So don't hesitate to stop me. Huh? That's the point of you being there, that there is interaction. Otherwise, in 40 minutes, I will be done. So tell me when you don't understand, okay? So at the moment, I will not discuss any statistical mechanics, anything. We just do a small course, a short course. Which book is the main source? The main source is the notes that I wrote. So if you check in the mail, there is a link, an overleaf link to essentially a small, to a 60-page notes that I wrote. You will find everything there, okay? But if you want to have other references, actually, if you check the mail of Roman, I gave some, but I can send again the mail. All right, so first definition. Okay, we'll take a very mathematical approach at the moment, definitions. So what do we call a finite discrete probability space? Okay. All right, so discrete probability space is composed by a set of what we call elementary events, okay, and a function that we call a probability. We will assume at the moment the simplest case, discrete probability, so the variables we consider take finitely many possible values and are discrete, you can count them, okay? We forget about the continuous setting at the moment, but everything I say can generalize to the continuous setting, of course, okay? But in statistical mechanics, actually, in many cases, it's sufficient to look at the discrete case, okay? At least in the models that I will consider during this course, everything will be discrete, okay? Because the point is to go towards applications of statistical mechanics to things that are not the usual statistical mechanics models, like algorithms, processing of bits in the numerical world and all that, and the numerical world is discrete, okay? So this will be sufficient for us. All right, so we have this set of elementary outcome and this function, and P is a function from this set onto 0, 1, okay? And this is called the probability distribution. And the only thing we require is that if we sum over all the elements of this set, of this function, it is equal to 1, okay? By definition of a probability. All right. Now what we call an event is essentially a subset of elementary events, okay? Of the probability space. So if you take any A, which is a subset, when you don't, I assume that if you don't stop me, you understand the notations. For example, that you understand this notation, which is included, okay? All right, so an event is any subset of the probability space, okay? All right, and how do we define the probability of an event? By definition, This is just the sum over all the elementary events that belong to this set of their probabilities. Okay? So this is less or equal than 1. All right. So can you think about a simple probability experiment? The classical example we give is what?
Coin toss.
The coin tossing. Okay? So, okay, so I have to get, okay, now what do I do? Yes. All right, so the coin tossing experiment is the most basic experiment you can think of. In this case, I will call sigma 1 the space of elementary events, which is head or tail. Okay? It's called tail? Yeah. Head or tail, yeah. Okay. What was the A? The A was by definition an event. It is a subset of the set of elementary events. Okay? All right. And so here I emphasize this index I, which means that we consider one flip, one that we toss the coin just one time. In this case, you get or head or tail. Okay? So now if you consider two tosses, what is the space of elementary events?
Omega 2.
Sorry?
Omega 2.
Yes, so omega 2
is equal to
is what? It's head, tail,
tail head,
tail, tail. Okay? And this, I can also call it sigma 1 cross sigma 1. And this cross, what does it mean? But this, by definition, is the set of pairs, let's say x and y, such that x and y both belong to sigma 1. Okay? This is what we mean by this cross here. Okay? Here?
Yes.
All right. And so we also call that, sometimes in mathematics, sigma 1 to the square. Okay? But really what it means is this. All right. So other properties that are just basic implications of the definition we gave about probabilities. Do you understand what does that mean? This symbol here inside the probability is the empty set. Okay? So the probability that nothing happens is 0. Okay? If you consider an experiment, something must happen. Okay? And the probability of the whole set of possible events, and sometimes I will also use another word which is outcome. Outcome or events are same things. Okay. What is the probability that of the whole space of outcomes? Which is 1. Okay? Because, okay, with what we said, this is just the probability of all the values in sigma. And by definition, this function is normalized. Okay? All right. Now, still a consequence of the definition we gave of what is a probability, we can also directly deduce that if you consider two events A and B that are disjoint, you understand what I mean here? So the intersection of these two sets is the empty set, so they have no element in common. What is the lowercase omega? The lowercase omega is an element of the probability space. Okay? It's an elementary outcome. Okay? So for example, in the experiment where you toss 2 times a coin, one little omega could be head or tail head. Okay? All right, so if you take 2 disjoint events, which means that they cannot occur at the same time, they have nothing in common, okay? Then probability of their union is what? By definition, it's the probability of all the elementary outcomes that belongs to this set, therefore the union. And because they have nothing in common, I can just first sum over the events inside A, and then sum over the ones in B. Okay? Just think about two boxes. If you want to sum over all the elements that are in the union of these two boxes, and they have nothing in common, just sum over the ones in the first box A, and then you sum over the one in the box B. So this, I can rewrite it as sum over W in A plus sum over W. Sorry, it's omega. I'm sorry, it's an omega in the notes. Okay, and this is P of A plus P of B. Okay. So how do we read in words this operation? So this is like the set information, the set theoretic way of defining probabilities. What we are doing, it's very clean mathematically, it's beautiful, but just in words, what does it mean, this symbol? How do you read that?
A union B.
Yeah, A union B, but what does it mean? It means A or B.
B or B.
Okay. This is the probability that A or B happens. Okay. While the probability, so this is the probability that A or B occurs. Okay. While if I would have written something like this, the probability of the intersection is what? Would you read that in words?
A and B probability.
This is the probability that A and B occur. Okay. Or this is the probability of the elementary outcomes that both belong to A and B. Okay. So let's try to think about an example. Let's define A as the set where the coin gives you 2 times the same result. So what is this set? It's head, head, and tail, tail. Okay? While B could be defined as the set where there is at least 1 time tail that popped up. Okay? So what would be this set? Tail, 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 head. Okay? So what is the probability? Sorry? Yeah, sorry, I missed one. Thank you very much, because there is an order here. The order matters. So head, tail. Thank you very much. So what is the probability that, so P A intersection B here is the probability that at the same time we have the same event occurring 2 times, okay, the same result 2 times, and that at least 1 time we have A. So in this case, probability of A intersection B is just the probability of tail, tail, okay? And if the coin is fair, what is this probability? Excuse me?
Can you repeat the question?
It's what?
Can you repeat the question?
Yeah, I'm asking if the coin is fair, it is a fair coin. What is the probability of this event?
1/4.
Yes, it's 1 divided by the cardinal of the space of all possible elementary events, which is 4. Okay? Because here all events are of a uniform probability. Okay? The coin is fair, so everything happens with the same probability. Okay? Sorry. All right. So more generically, if I take some sets, okay, so that for each pair of sets, their union is the empty set. So all these sets, they have nothing in common. So I take a family of sets like this, okay? So that their union, they are pairwise, they have nothing in common pairwise. Okay? So all these sets, it's called a partition of the space. Okay? A partition of the space, it means that you take, for example, the space of all possible outcomes of your random experiment, and you divide it in subsets with nothing in common. It is called a partition. Okay? You are partitioning the space. So if I take a partition, which mathematically means that if you take any two such subset, they have nothing in common. Okay? And I look at the probability of their union, A1, A2, union. There are n of them. What is that? It is the sum, indeed, of the probabilities. Okay. And from this, you can deduce directly from this rule I just wrote, okay, and from the fact that by the definition of the probability of the whole space is 1. Oops, change this color without asking. Okay. We know that we can decompose what is the simplest partition of the space into non-trivial subsets. It's just in two subsets. You divide your set in two subsets. Okay? So if I take any A, I can divide the space in A union what we call the complement, means the rest, what is not A. Okay? So this is the complement of A, which is also sometimes denoted with a C, like this, or complement. Okay? And so A and the complement of A, by definition, their intersection is the empty set. They have nothing in common, by definition of what the complement is. Okay? So the complement, if you want, it is also defined as the whole space where you remove A. Okay? So this bar here notation, it means that you take a set and you remove from it another set. Okay? It's like the minus operation for sets. So the complement of A is defined as the whole space of possible outcomes minus the ones that belong to it. Okay? And so this we know that it is the probability of A, because they're disjoint, so these two notations are the same thing. And therefore, it implies that the probability of not A, that A does not happen, which means the probability of the complementary set of A, is 1 minus the probability of A. Okay? Very simple. Is all that new, or is it not new?
Not new.
Or is it the complementary of new?
Complementary of new.
Okay, well that is not a surprise. Okay, okay, that's great. But anyway, I want to say all these things so that you know we have the same language. Okay. I won't then in the rest of the course each time define a probability space and be very precise, but underlying what I will say, there is all these notions that are there, okay? And having that in mind will clarify the rest, especially when I will define the notion of entropy, which is the key notion we want to understand this week, okay? And you will see from the entropy what is magic is that will deduce the Gibbs-Boltzmann distribution that you understood how to get from the canonical ensemble in statistical mechanics. We'll get it in a totally different way, a very beautiful way of doing it. without calling ensembles and things like this. All right, I'm a bit slow. I need to speed up a bit. So definition 2, what is a random variable? All right, so we have the probability space, which is a space of elementary outcomes and a probability. Okay, so random variable x, so here I need to use, I need to be careful in the way I wrote things, with possible outcomes little x. So when I use a capital letter, it means the random variable. When I use a small letter, it means an outcome of the random variable. So for example, in the coin tossing experiment, the random variable is head or tail. Okay, it's the result of this experiment. While an outcome is that you actually do the experiment and you observe head, for example. Okay, it's fixed. While the random variable is random. Okay, so we have a random variable x, big X, with possible outcomes little x that belong to a space calligraphic X, which is the space of possible outcomes of this random variable. Okay. And what it is a function from the set of elementary outcomes onto this space of possible outcomes of this random variable. Okay. So can you give me an example in this? Let's say you toss the coin 2 times. Can you give me an example of a random variable in this experiment that we could be interested about? A random variable could be. Did we get?
Throwing dice.
Sorry.
Throwing dice, for instance.
I didn't hear, I'm sorry. The dice experiment, yes, the dice experiment, it's similar to the coin experiment that we're talking about from the beginning, so I will stay on the coin experiment. Okay, so think 1 second about that. I finish the definition and then we try to find an example. Okay, try to find any random variable connected to this experiment where you toss a coin 2 times or 3 times, whatever you want. Okay, let me just finish the definition and then we come back to the example. So it's just a function from this space onto another space, and we call the probability that the random variable capital X, that you observe the outcome little x for this variable big X, that we also note like this to be more explicit, but it means the same, is the probability of a set. From the beginning, the only thing we define are probabilities of sets. So what is this set? It's the set of all elementary outcomes such that, or I was using this notation, this means such that this function evaluated on this elementary outcome gives little x. Okay? So it's a very natural definition. Okay? You just look at all elementary events that lead this random variable to take some fixed value little x, and you look at the probability of this whole set of elementary events. Okay? Is it clear? And so, what is it? Because elementary outcomes, by definition, they are disjoint, okay? Different outcomes. This is just the sum over all the W's that belong to this set, such that this function gives you little x. Okay. So you have an example in mind. Say we toss the coin 3 times. to make the space of elementary outcomes a bit richer. Okay? Can you think about random variable? Anything?
These two heads.
Yes, so you read my course. That's good. So indeed, a random variable could be, do we get two heads? Okay. So an example, X could be, or no, let's say the number of heads in 3 trials or tosses. Okay? This is a random variable. Okay? It's a function from the space of all possible elementary outcomes. Here, all the possible elementary outcomes are what? Head, 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 tail, head, tail, etc., etc. Okay? So it's sigma 1 to the 3. I can call sigma 3 also. Okay? Which is what? Which is head, 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 tail, head, tail, tail, and so on and so forth. Okay? By the way, what is the cardinality of this set?
The total of heads.
So cardinality of a set means the number of elements inside this set.
Yeah.
What is the cardinality?
8.
It's 8, yes. Because, okay, each of these coin has 2 possible outcomes. So it's 2 times 2 times 2. Okay? 2 to the power 3. So sigma 3 is 2 to the power 3, which is 8 indeed. Okay? So what is, let's say, so we said that this X, this random variable, is the number of heads. So what is the probability? What is the probability, let's say, that X is equal to 1? So we say it's the number of heads. So it is which set? It's the probability of the set where each time you have a single head. So it can be head, tail, 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 head, tail, yeah, and tail, tail, head. Okay, and all coins are fair, so this is just 3 over the cardinal of the set, which is 8. Okay? Very easy. All right, now all that is the underlying structure of discrete probability, okay? But often in applications, you don't define an actual set of elementary outcomes and all that. You don't need to do that. You directly work with random variables, okay? Which might be just what interests you. You do not care about what are the elementary values. So, one convenient definition, which allows us to directly work with random variables without caring about all these details, if you want, but which are there in the theory, which is the definition of an ensemble. Okay? So, what I will call an ensemble associated to a random variable X is a triplet composed by a random variable, its space of possible values, and its associated probability. Okay? Okay, and of course, we have that the sum over all the x's, the outcomes of this random variable is 1. Okay. And of course, any probability is a positive number. I said it from the beginning. Probability is something between 0 and 1. If you sum over all possible x's, in this case we have. Okay, so it must be normalized. All right, so often we'll directly work with an ensemble. So I will say this is the variable we are interested, and this is the associated ensemble. Okay. So in statistical mechanics, for example, what are the elementary outcomes? What is the natural notion associated to that? That you heard about already?
Temperature.
Is?
Temperature.
The temperature?
What?
No.
The energy.
Is what?
The energy.
The energy? No. What are the most elementary description of the system? To consider statistical mechanics systems, what is the
Microstate?
Yes.
Microensemble?
these are the microstates.
Microchem.
Okay? So in statistical mechanics, the elementary event is the set of all possible microstates. Okay? Okay? And what could be a random variable? Often we consider what we call the random variables that we are mostly interested in are called order parameters or observables. Okay? These are the quantities that you can measure as an experimentalist in a lab, like the magnetization or the correlation length, all the physical properties of the system that you can measure, and that are of course functions of all the microstates. Okay? And these are random variables, these order parameters. Okay? They fluctuate. Okay?
The random variable state.
The random variable is a description of the state through some quantities that we call observables or order parameters. Okay? Which are, you as a physicist, what you consider as a valid description of the system. These are the quantities that you are interested in. Okay? And these are random variables. They depend on which specific microstates the system is in, but you do not care about the microstates. What you care about are these macroscopic variables, which are random. Okay. You seem, is it okay or you're, you process? Okay, so think about it. All right, so now a very important operation that we use all the time is the expectation. Okay, I will use that 100 times a day. So given an ensemble that I just defined above, how do we define the expectation with respect to the random variable x of some function of this random variable? That we also like to note with the statistical mechanics notation like this. Okay, and if we want to emphasize that the quality distribution associated to this random variable is P, maybe we can index it like this, just to make sure we know what is the quality associated to this random variable. Okay, is what? This is the sum over all possible outcomes of this random variable of P of x, G of x. Okay? All right. Sometime I will be a bit more loose on the notations, and instead of really writing this, which emphasizes that this little x is an outcome of the random variable big X, I will just write this, which should be clear, because anyway this little x must be associated to the associated random variable, which is big X. Okay? Or that is the same as this. Okay? You should get used to this notation. Okay, because this is what I will mostly use. Okay? All right, so further definition, don't worry, we're almost there, is the definition of a joint ensemble and joint probability. So joint ensemble, and by joint I mean it's the ensemble associated to a pair of random variables, or it could be more, okay? Of course, once you have the definition for a pair, you can take a pair of pairs, you get 4 random variables, or etc., etc., okay?
So,
Yes?
yeah, since you say the random variable is the measurement, what you say?
Yes, so if you measure something, some quantity, let's say the magnetization in some magnetic material, to measure it a priori, but what you measure is random. Because the system is large and will be in the thermodynamic limit, what we'll realize, and that's all the point of statistical mechanics, is that this thing will not fluctuate. You will measure something which is fixed, but a priori, it depends on all the microstates, and if you had a perfect apparatus able to measure very small fluctuations, you will realize that this magnetization evolves in time. It is random, because it depends on the fine structure of your system, which is the microstate.
Okay. Let's say we need to repeat this operation n times.
Which operations?
We measure at first one, and then we measure again.
Yes.
Again and again.
Yes.
That means the number of times we measure the situation is the number of days in our days. Since we say, okay, we have the output which belongs to R, N. And here is the number.
No. You're saying Rn like this. So here Rn would be the space of elementary outcomes of your system. It would be, let's say, if you consider statistical mechanics models where you have particles living in a box, let's say, or even in the whole space, like it's Rn. You have n particles. They can take any position in the space. Okay?
Yeah, we have n particles.
Yes.
And the random variable here is the word. Because since we have the random variable capital X. And
no, but here the definitions I'm giving are generic definition. I'm not talking about a specific random variable.
okay.
Yeah.
I think he's confusing it with the first part.
Yes.
So a random variable would be, for example, if there are n particles in this given space, right? So perhaps we can measure the temperature, right? Because we can.
Yes.
That's an observable. We can actually.
So it
measure.
depends on which ensemble you consider.
Yeah.
Usually the temperature is what we call a control parameter. It's something that as an experimentalist you fix.
Yes.
Okay, but for example, you could measure the internal energy.
Or
if you consider a magnetic system, like spins,
Yeah.
okay, an observable is the magnetization, the global magnetization of the system. And this is a random variable.
Or the excitation energy.
Yes, you can think of infinitely many different random variables for a given system, but for example, consider a spin system. Okay, we're going ahead here, but consider a spin system. So the space of elementary outcomes, let's say you have n particles, which are just spins, binary variables. The gamma is -1 to the n. Okay. Is that clear already?
Yeah, and it's the number of particles.
Of spins, in this case, yes. And one possible random variable, which is therefore a function of this space to another space, could be the magnetization. If these spins are this xi, this could be defined like this. This is a function from minus 1, 1 to the n on 2 in this case. So m in this case would be a function from gamma on 2, let's say on 2 minus 1, 1 in this case. Okay? So it's a random variable because it depends on the specific value of all these spins, which are random. And that's it. Okay?
It's random because it depends on a random configuration?
Yes, exactly. This magnetization depends on the configuration of spins, which is random, because it fluctuates according to the Boltzmann distribution and all that. We will come back to that. We are ahead. But here, yes, the spins are random variables, they fluctuate. And if you measure the magnetization at some time, it will give you a value. And maybe if you measure right at 10 seconds after, it will be different. Because the spins are fluctuating, they're random variables. Okay? So here the elementary outcome is the space of configurations of the spin. And the random variable associated here would be the magnetization, which is a function that takes an elementary outcome and outputs a number, in this case between minus 1 and 1. Is it clear? If it's not, just say no. I assume that.
I'm just curious why it's called random. Like, for example, for those, sometimes they follow a rule for their configuration, so it's not totally random. Never mind.
So they follow rules, so it's not totally random. In statistical mechanics, we describe always a system thanks to a probability distribution. At the moment where you decide to describe your system using a probability distribution, it's because your system has some randomness. There is something you cannot predict about it. So what I'm going to say now is what I want to say in half an hour if I'm able to continue. But essentially, even if you have a deterministic system like particles that are, actually there is nothing deterministic in physics because the world is quantum, but let's say that we'll consider classical particles that do not follow the quantum mechanics. Let's say these are just small balls moving around in a box. Okay? Even if, in theory, the system is deterministic, if you have many, many such particles, the system is so complex, and actually you do not care about the individual trajectories of these particles. So what you do is instead you consider it random, and you associate to it a probability distribution, which allows to describe the system using statistics and to access what actually matters, which is a macroscopic description of the system. And what do we mean by macroscopic description? We mean values of some specific random variables, like the magnetization. These are called order parameters. It's the random variable that you define as relevant to describe the system of interest. Okay? So for example, if you take a fluid, you start to change the temperature. Below some temperature it will be solid. Okay? Then above some temperature it will be a gas. You do not care about the position and the trajectory of each particle. These are the microstates. These are the elementary outcomes. You do not care. What you care is whether if you are in the solid, liquid, or gas phase. How to describe that? Thanks to a random variable that could be the correlation length between the particles or the local density of molecules. If this random variable, it's random because this depends on which particle are where. But let's say this local density is very low, then you can define your system in a gas state. And below some temperature, you will realize that this random variable becomes higher. You are in a liquid state, and suddenly it's even higher. You are in a solid state. Okay?
I have a question.
Yes.
So if, for example, we consider plasma.
Yes.
Plasma exhibits macroscopic properties that are different from its microscopic
Yes.
properties.
So the density is very low, and the particles.
Yes, but it's like the quasi state, right? Because the particles have. I mean, the definition of a plasma is very different. So how do we have a different methodology for that, or
The question is not clear, answer.
In a plasma, the microscopic properties are quite different, and that's what matters, rather than just the macroscopic properties.
No, the macroscopic.
Because macroscopic as a whole, it's stable, it's at equilibrium.
Yes.
Yes, but the microscopic.
Yeah, but if you measure some macroscopic property of a plasma, which is at equilibrium, what does it mean? It means that at equilibrium, it means that these order parameters, they do not fluctuate, they're fixed essentially.
Yeah.
But now if you go from plasma to gas or to another physical state, and if you place yourself in the gas phase, but you don't change the temperature anymore, you will see again that these same parameters are again fixed, but to another value. And this is what distinguishes gas and solid and the plasma, for example. At equilibrium, these order parameters, they do not fluctuate at our scale. Okay?
Yes.
Okay. But if you change some control parameter, like the temperature, this will change. You enter a new phase, but then if you stop changing the temperature, the system equilibrates. You measure again this property, this random variable, and it will be fixed to some value. Okay? But what you should understand is that even if at our scale, if you measure it with an apparatus, it looks constant at equilibrium. Actually, if you were able to measure very small fluctuations, if you had an apparatus extremely precise, you would observe that this quantity fluctuates a bit, a tiny bit. And this tiny bit comes from the fluctuations of the microstates. Okay? But at our scale, these fluctuations are so small that we don't see them. Okay? These fluctuations actually in statistical mechanics, usually if you take any order parameter, any global quantity defining the system, it fluctuates of the order of the variance is 1 over n. Okay? So if n, the number of particles, is large, is 10 to the 24, the Avogadro number, you see that the fluctuations are negligible. So the system looks totally not random. It looks totally still, but actually they are small fluctuations. They're just very small. But the magnetization or any other order parameter, any quantity you measure about some system is actually fluctuating, but just a tiny bit. Okay. Okay, this was a parenthesis. I will come back to these things. So, I wanted to define now a joint ensemble. So, joint ensemble is again a triplet. The first thing is a pair of random variables, which is ordered. Okay. Then, it is a product space. It is the product space of the individual space of each random variable. Okay, so now this notation should be clear. I will say again what it means. And it's a joint probability. Okay, so this is what? This is the set of little x and little y such that x belongs to x and little y belongs to y. Okay? It's called the product space. Okay? So we have our joint ensemble. So the cardinal of this thing, of course, is just the product of the cardinals. Okay. And we call this object the joint probability. Okay? That's it. It's just a function that takes an element from this product space, and that gives you a number between 0 and 1. Okay? That takes an element from the product space that outputs a number between 0 and 1. Okay? So if you want, you can see this pair of random variables as a single random variable. You can call a couple of random variables just a new random variable. If I want, I can call Z this pair. This just defines a new random variable. Okay? It's just that we define this joint ensemble because sometimes we have two different random variables and we want to associate to their couple a probability distribution. And so we need this notion of joint probability distribution that describe their behavior, their random behavior, together. Okay? So, for example, in the coin tossing experiment, let's say that you toss the coin n times. One random variable could be the number of times you get head, and another random variable could be sorry.
You get at least one.
That you get at least 35 heads.
Yeah.
Okay. And these two random variables, there are two objects, okay, that fluctuate, that depend on what you will get for these n tosses. But maybe you want to know what is their joint law, their joint probability distribution. What is the probability? How do you read this object? The probability x, y of an outcome of this pair, which means of x and y, okay, which I will also denote simply like this with our shortened notation. What does it mean, this in words? This is the probability that x takes value, or let me say x's outcome is little x, and by n it means at the same time y's outcome is little y. This is what it means. It is their joint distribution. What is the probability that jointly, which means at the same time, we observe little x and little y? Okay? Is it clear? I see many things on the chat, but maybe 10 minutes too late. No. I'll keep it up. All right, next slide. Very useful definition of independence. What do we mean by two independent random variables? By the way, in probability, sometimes we write this. If x is independent to y, we use this symbol. It's like if they're orthogonal. They have nothing in common. Okay? What does it mean for random variables to be independent formally? Now we have a definition of the joint law. We know what a probability is. By the way, I'm sorry, I wanted to add something in the previous slide. This joint probability, so this is called the joint probability, should be normalized. It is a probability. What does it mean? If I sum over what? Yes? Yes, so I must sum, if I sum over all, if you want, if I see this pair as a single random variable, if I sum all of p of x, y, which is the same as writing sum over all x in x and y and y in y of p of x, y, this must be 1. Okay? It's clear? Okay. Don't stress if you miss something. All that is written in a lot of detail in my notes. Huh? So go for it.
The chapter is covering the
So what does it mean for random variables to be independent?
The intersection. There's no intersection.
Speak louder.
There's no intersection.
There is no intersection.
There's no joint.
Like they don't depend on each other.
So when you talk about intersection, I'm okay because random variables were defined. If you define a space of elementary outcomes, a random variable, the probability of a random variable is the probability of a set of elementary outcomes, so that this random variable takes some value.
Mm-hmm.
Okay. So if you use this language, so what is independence there?
I think the value of y does not depend on the value of.
Yes, but
Yes. So their value are independent, but how do we formalize that? So I give you a hint.
Correlation?
I just defined here the notion of joint probability.
mm-hmm.
It starts from that. It is a special independence implies a special property of this joint probability, which is
0. The joint, not okay. So in the joint probability, x and y, the random variables might be dependent or independent. We don't know. But if they're independent, then if you go back to the definition of two separate variables, a and b, probability of a plus probability of b, that's the disjoint probability, right? So there is no dependence between a and b. A does not depend on b in that way.
so how do you write that mathematically? So I vaguely grasp what you mean. I feel that you have a sense of it, but so this is a generic comment. So now you are doing a degree in theoretical physics, and you need to make the effort when you say something to formalize it using mathematics, because this is what theoretical physics is about, right?
Okay.
The point of becoming a physicist
Through multiplication?
formalize things. So how do you write that using the definitions that we introduced from the beginning? Yeah, I hear someone, yes? It's
Through
Anna,
product?
yes.
Multiplication?
Multiplication.
The product, yes, this is what I wanted to hear. So two random variables are independent if and only if, which means it's the definition of independence, okay? If and only if the joint law factorizes, and here I will use a new symbol, okay? But this symbol looks fancy, but it means nothing else than the probability of xy is equal to the probability of x times the probability of y. And here, again, I'm using the shortened notation, but here what does it mean? It means that the joint law of this pair is just the probability of x taking value little x, and the probability that times the probability that random variable y takes value little y. Okay? So the joint law factorizes. Okay? When I say law, I mean probability distribution. Okay? When you're doing probability and you say a law, it always means the probability distribution. Okay? This is the law of x. Okay? This is the joint law of x and y. Okay? It's just that it's faster to say law than probability distribution. Again, we're saying it 100 times in a course, so if you gain 1 second each time, you're happy. Okay, that's all. So low is a quality distribution. All right. And in this case, we write the joint ensemble like this, which means what? It means, the triplets, which is again the pair of random variables, their product space. This does not change. But now the joint law is what? It's just the product of their individual laws. Okay? This is just meaning that I'm considering this property. If I want to evaluate the joint probability of x and y, I just multiply their individual probabilities. This is what.
So does that mean that joint probability is equivalent to independence?
Say it again.
Does that mean that independence is equivalent to the joint probability that we did earlier?
No. Here, in this case,
yeah,
maybe the two random variables are not independent.
Okay. In that case.
So, for example, if let's take the extreme case. We still have this. We toss the coin n times. Let me consider one random variable, which is the number of heads. Okay. And another random variable, which is the number of tails. These random variables are there independent. Yes? Why yes?
No, in n times?
Yeah, let's say you toss the coin 2 times. Okay, or n times, it doesn't matter. 2 times. One random variable is the number of count that you got head. It can be 0, 1, 2. The other random variable is the number of tail. That could be 0, 1, 2. Are these two random variables independent?
No.
No. So who thinks it's independent? Who thinks that they're correlated? So correlated or independent?
Correlated.
Correlated.
Independent.
Independent. Independent. Why independent?
Because having any outcome doesn't affect the other one, the next one.
But that's not true.
That's not true.
Imagine that you observed in one single experiment where you toss the coin 2 times, you observed that you got 1 time head. Can't you infer from that what is the number of tail?
Yeah.
Okay.
Yeah.
You seem lost.
Yeah.
Why?
Since you choose 2 twice, right?
Yeah, if you want 2 times, yeah.
Yeah. When I choose the first time, I can get head.
No, but the experiment is you toss it 2 times, then you observe what you got. Okay? You observed that I got head, tail, for example. This is the result of the experiment. Okay? Now, you see that if you can count, so this result of the result of this experiment was random. Okay? You observed some outcome. Before observing this outcome, you had in mind 2 random variables. One which was the number of head, and one which was the number of tail. Now you observe this result. So you can say, you just look at what you got, let's say 1 time head, 1 time tail. You can count the number of heads, it was 1. Can't you deduce from that what is the number of tail? Of course you can. It is 2 minus 1, 1. So these 2 random variables, they are the opposite extreme of independent. One is a deterministic function of the other.
Yeah.
If I give you the outcome of one of these 2 random variables, you know for sure what is the outcome of the other. Is it clear? Okay, can you give me another example? Forget about coin tossing. Think about whatever you want. Give me two random variables that are totally dependent on each other, in the sense that one is a deterministic function of the other. Think about whatever you want.
Pick two students. If you want to pick two students.
Yes, so you pick two students, okay?
So the pick is male or female.
Sorry?
Male or female.
Okay, so you define, so the space of possible elementary outcomes are
male or female.
Male, female, male, and female.
Yeah.
But you're doing the same experiment as coin tossing. You are considering two binary variables. This is the same as the coin tossing experiment. Instead, you're saying male and female, but that's the same. Think about something else. Try to think out of the box. You know, you can use probability to describe whatever you want. Let's say, I don't know, one random variable is the professor entering the room or not, and the other random variable could be there is a course or not. So these two random variables are strongly correlated. If you see the professor entering, it means that the course will start. Okay? So they are not independent. Can you think about something else?
What about the email?
Okay.
Spam. I received an email. It's spam or not.
Okay, so this is one random variable. What is the other?
The first one is to receive.
Okay.
The second one is it spam or not spam?
But where is the correlation here?
First, you need to receive. If you don't receive, you can't know if it's.
Okay, so you mean one random variable is receiving or not a mail,
Yeah.
and the other is, yeah, but the thing is that you cannot define that it's spam or not. You do not condition on the fact that you already received a mail. So you must receive a mail to say if it's spam or not. So you say it's. Or let's take another example. Let's not consider two.
Okay, I have an example, but it's not the extreme correlation.
Perfect. Give me two correlated random variables.
So maybe, okay, it's raining or it's not raining,
Yes.
and there are clouds and there are no clouds. So if it is raining, we can make sure that there are clouds.
Yes, that's a very good thing. And you see here there is a direction. If it's raining, it is deterministically the case that there are clouds. But if there are clouds, it doesn't mean that
it's raining.
You see here that's a very good thing. You see that sometimes if you consider two random variables, the order in which you observe one and the other matters. This is what I meant here by this is an ordered pair of random variables. So sometimes there is an ordering. In this example, there is an ordering. Okay? So yes, that's a good example. Here, the joint law of the random variable x, which is it rains or not, and y, which is there are clouds or not, does not factorize these two random variables. They have a joint law. They have a joint probability distribution that you cannot write as the product of their individual probability distribution. Okay? Okay. Now can you give me examples of independent random variables, or that are very naturally considered independent? Let's say you buy a ticket for a tombola, and the fact that you win or not is a random variable. Again, a binary random variable. Okay, you win or you do not win. And another random variable is the weather. If it rains or not. Do they have a joint law? Are they correlated? A priori, no. It is very natural to think that the weather does not influence the fact that you will win or not at some game. Okay? So these two random variables, they are independent. Okay, knowing one does not bring information about the other, and vice versa. Okay? Now, what I want to, okay, so we have a notion of independence. Now the answer, the question I want to ask is, imagine that you have a joint law for a couple of random variables, or more of them, for 3, 4, 5 random variables. Okay, you can, from the definition I gave you, you can extend to any number of random variables. Can you deduce from a joint law, a joint probability distribution, the individual probability distribution of each single variable? So let's say that you have X and Y, they have a joint law. You have X and Y, they have a joint law that you know. Can you deduce from that what is P of X, for example, or P of Y?
Yeah.
Yes? So, yes, I agree with you. How do you know that?
I already.
Sorry?
I read something about
So what did you read?
yesterday.
You read something about that yesterday?
In your notes.
In my notes. Okay, that's good. So this procedure is called marginalization. So what is a marginal law? So the marginal Px of x is simply obtained. So by marginal here, we mean that we start from a joint law and we go back to the law of a single random variable. And when we do this operation, we call the probability of the single random variable the marginal. The marginal probability means that we started from a joint law and we go back to a single of them. This operation is called marginalization, and the result is a probability distribution, and it's called the marginal distribution of x in this case. So what you have to do is simply to sum over all the elements of y of the joint law. Okay, and you can of course change x for y. Huh? You can do the you can get the quantity of y summing over x. Okay, and this is very natural. This is the joint law of, this is the quantity that x and y, that the random variable x takes outcome little x, and the random variable y takes outcome little y. Here we are fixing little x to its value, to something, and we are summing over all the outcomes of y. But x is fixed, so we are just summing the probabilities. We are looking at all possible events for y. We see the weight, the probability that it has when the other variable is fixed to little x, and we sum all that. It's a very natural operation. Okay? Okay. So here, exercise, try to think about a natural example of marginalization. Take the coin tossing experiment or whatever experiment you want. Define some pair of random variables. Okay. Define their joint law and get the marginal distribution for one of them. Okay. Try to think about it. Okay. But this operation should be natural now with all what you said. You just sum over the other variable because it does not matter. You do not care what value y takes because you only care about what random variable x takes. To just sum out the y. Okay. Okay. another definition. So if you wonder, yes, these definitions will be useful. No? Not all of them. Some of them are there for you to have the concepts, but some of them will be useful directly in this course. So now, consider a pair of random variables. Okay, we define the conditional probability of x given y. This is to be read probability that x takes value little x given, or this can be read also conditional on y taking value little y. So here it means that the outcome of y is fixed. We observed it and it is fixed. Okay? Given that this random variable y is fixed to some value, what is the probability that the other takes some other value, little x? Okay? This is, by definition, the joint law divided by the probability of y. Okay? And of course, this definition is symmetric. You can change the role of x and y. And with what we know about marginalization now, this can be also written. The denominator here is what? Is the marginal of y, which means the sum over x of the joint law. Okay? So let's take the coin tossing experiment again. Okay? Let's say that one random variable is we toss the coin n times. One random variable is the number of heads, again, independently of the order, just the number of times we got head. And another random variable is that it's a binary random variable that is equal to 1 if the number of heads is more than n over 2, and it is 0 else. So this random variable tells you if you got more than half of the toss that are head. Okay, so let's say x is the number of heads, and y is the indicator function of the number of heads being greater than n over 2. Okay. So let's say, and this belongs to 0, 1. You know what is the indicator function? You know what is this function here? Okay, so the indicator function, if you write this, the function that is equal to 1 if A is true, 0 else. It's just a function that tells you whether something happened or not. Okay. So this random variable just tells you whether you actually got more than half of the tosses that were head. Okay? Then, what is the probability that x is equal to, let's say, 3n over 4, given that y took value 0. Okay, so the random variable x belongs, takes value between 0 until n, if we have n toss. So what is this probability here? It is equal to 0. Okay? Given you know that you got less than n over 2 heads, the probability that you get 3n over 4 has to be 0. Okay? It's clear? Good. Okay, now if I was putting here in the exercise for you, if I give a 1 here instead, what is this, how this number is changing? Maybe you can try to think about that. Okay. All right. This conditional probability, in which sense it is a probability? What I mean by that is it is a probability for the pair xy. Is it a probability for y, or is it a probability for x? And again, when we say a probability, we mean something very basic. It's a probability is an object, it's a function that takes values that output a number between 0 and 1. And so that when you sum over all possible entries for this function, you get 1. It is normalized. So my question here is, in which sense is it normalized? It is a probability distribution for x, xy, or y?
xy.
xy? So you mean that if I sum over all the possible x and y here, I will get 1?
You should, yes.
Speak loudly.
You should, yes.
No, just look at the definition. If I sum over x and y here, do I get 1? No, I don't. So so it's not a probability over x and y, because it's not normalized if I sum both over x and y. But is it clear that if I sum over x and y, it's not 1? Yes or no? Okay, I see you looking at them, which means no. Okay, just take, for example, this definition here, which is equivalent to this one by marginalization. Okay, because this denominator is the same as that.
Can you write on the right side of the board so we can see?
Yes, so if I sum over x and y here.
But the thing is, they can't
They can't see.
We can't see the board.
What?
They can't see.
Ah, I'm sorry. If I sum over x and y here, do I get 1?
Oh, okay. No.
Yes or no? I don't get 1. To get 1, I need the numerator and the denominator to be equal.
Yes.
So you see that at the denominator and the numerator, the difference is that the denominator has been summed over x only, not over y. So this denominator here, this denominator is a normalization with respect to x only. You see that it still depends on y. Because here we see that the interpretation is that y is fixed to some value little y. The random variable capital Y has been fixed to some value little y. So it is fixed. If you want, it's like a parameter of the probability distribution. But really the randomness here, the random variable is x. And the way you see it is just that this denominator here, you just have a sum over x. So if I sum over x only, Yes, now the numerator and denominator, they simplify, and you get 1 independently of the value of y.
Oh. Yeah.
Okay?
But that will change if we fix x. Then it will become dependent on y.
If I switch the role, if here I put y given x, here I put y, and here I put x, yeah, the role is symmetric, then it becomes a probability distribution over y.
Okay. Yeah.
Of course. Of course, x has no, I'm using each time, I'm conditioning on y, but you can reverse the role. I mean, x and y are just two abstract symbols, okay? So you can change their role, okay? So this is a probability distribution for the random variable y. For the random variable x, okay? Is it clear? If you sum this thing over y, what you get is a sum over y here. Sorry, actually, both the numerator and denominator depends on y. This is not equal to 1. This is something, it's a number, which is positive, for sure, because the numerator and denominator are positive, or at least non-negative, but that's all. It's not equal to 1. So really, this object is a probability over x, okay? Proba for x, for the random variable x, okay? And really, this symbol here, this bar, what you should keep in mind is this meaning. Oops, what happens? It's this meaning here. This bar is called a conditioning operation in mathematics, but in words it means given the fact that we observed the outcome little y for the other random variable. Okay? So let's think about the conditional probability. What is the probability that you have a good day, which is a random variable, given that the weather is nice? It is higher than when it is not. Okay? Okay? Or what is the probability that you have a great year and that you become an amazing scientist in the future, given that you work a lot? It is close to 1. Okay? But the fact that you work a lot here is a random variable. Maybe you will not work a lot. I hope you will do, but right now we don't know. It's still random. Okay? But if we assume that you work a lot and that at the end of the year you did work a lot, the probability that you make it in science is higher. Okay? Is it clear? Okay. But here it's a probability over the random variable making it or not in science. It's not a probability on working a lot or not. This is something over which we condition. We fix this, and then we consider another random variable conditioned on this fact. Is it clear? Can you give me another example? You should always try to find examples. This is how we understand things. What could be an interesting conditioning for some random variable? Be original, think about anything. I mean, anything can be described with probabilities, so just think about something.
So maybe the probability of me getting COVID given that I do the safety measures?
Yes, is low.
Yeah.
The probability probability that you get COVID given the fact that you are safe, that you're cautious, will be much lower than if you're not. Okay? All right? All right. Last thing. So often I will just write things like this. Okay? I will not choose much, but the shorter notation is like this. The probability, here this means the probability that the random variable big X takes outcome little x, given that Y is fixed, is conditioned on taking value little y. Okay. Okay, so last definition, well, it's actually not a definition, it's a property that follows from the definition of conditional probability, which is called the product rule, which is simply rewriting the definition of conditional probability in this way. Probability of x and y is simply the probability that x happen given y times the probability of y, and by symmetry this is also the probability of y given x times p of x. Okay? So how to read that in words? What is the probability that both x and y occur? It is the probability that y occurs, this is this term, independently of x, independently of anything, times the probability that that x occurs, given that y occurred. Okay? Okay, so what is the probability that you make it in science and you worked a lot? It is the probability that you made it in science given that you worked a lot, times the probability that you will actually work a lot. What is the probability that you get the COVID given that you've been cautious? Sorry, what is the probability that you get the COVID and that you are cautious? It is the probability that you get the COVID given that you are cautious times the probability that you are indeed cautious. Okay? If what I'm saying right now is less natural than the definition of conditional probability that we discussed here, you just take this relation, you put the P of y, you put the P of y here and you put it there, and you get the product rule. Okay? This is just rewriting the definition of conditional probability, but putting the denominator on the other side. Huh? There's nothing else. Huh? But it gives writing things differently sometimes allow to interpret things differently also. Okay. All right. And this implies also a very important, just by rewriting things again, where is the black? Differently. I write property because this is again an implication, it's implied by the definition of conditional probability. This is called the Bayes law or Bayes formula. It says that the probability that x is observed given that y has been observed, and by observed I mean that the outcome of the random variable big Y is little y, okay, is what? It is the P This is the probability that y happens given x times probability of x divided by probability of y. Oops. You see that I just rewrote the same thing as here. Y, is it the same thing? Why is it the same thing? It is the same thing because you see that if I take this thing and I put it there, I obtain this equality. Okay? So from the definition of conditional probability, we obtain the product rule. By symmetry between x and y, we obtain this equality here. And now by taking one of these two guys, or let's say in this case the p of y, and putting it on the other side of the equality, you get base formula. Okay? These are very basic manipulations. You divide and multiply. Okay? But you could say, okay, that's nice, but why rewriting this thing in this form if it's equivalent to the product rule, which is a fair question. But here, the interpretation, again, like we said, when we write things in a different form, the interpretation may sound different, maybe more natural. And here, the interpretation is actually extremely powerful. It tells you that the probability, so let's take let me phrase that. I mean, I will just say that in words. The probability that you observe x given that y is something can be written the other way around. It is just the probability that y was something given x was equal to x times the probability of x. But what I want to give you is an example. It would be more. Okay, let me tell you in which context this formula, this interpretation of conditional probability, because this is just a consequence of the definition of the conditional probability. Why is it so useful? It is useful in the context of what we call inference. So inference is, what is the process of inference? Is that you have data about some system and you want to understand something about the system from the data. Okay? So let's say that you have still this coin that you're tossing. Okay? And what you would like to know is whether this coin is fair, whether it is not biased. Okay? So fair means that it has same probability to fall on head or tail. Okay? So some data, so in this case, you could define x to be the random variable x to be 1 if coin is fair, 0 else. Okay. So again, like we wrote that before with our notation, this is an indicator function of the event coin is fair. Okay. All right. So how would you naturally answer this question? What would you do to know whether a coin is fair or not? What is a natural experiment?
You check both sides, or you toss them.
What you do is you toss it many times, and you look at the statistics.
Yes.
Okay? And which statistics do you look at? The number it fell on head divided by the total number. And this should be, if the number of toss is large, it should be a good approximation of the probability of falling on head. Okay? So in this case, the data, which is also a random variable, would be the number of heads divided by the total number of tosses. Okay? This would be your data. Okay? And the data is fixed. You set up an experiment, you measure this data, you get it, you get a number, and then it is fixed. You cannot change it. Okay? And with this base formula, you see that now you have the proper way to associate the probability to whether this coin is fair or not, given the data. So this probability in this case is the probability that you actually measured it is the probability that you actually measured some number. Let's say you measure the number of heads was 90% of the tosses. What is the probability that you obtain 0.9 given that the coin is fair? It is a small number, okay? And this probability is what we call the a priori probability. This is the probability that the coin is fair or not, independently of any data. And if you have no data, this probability is 1/2, 1/2. Essentially, you know nothing about this coin, so you just set it to 1/2. Okay. So this formula tells you what is the probability that something happened given data about it. It is actually the probability that this thing you observed does happen if you consider the unknown some value. The unknown here is the x times the probability that x happens independently of everything. And then this p of y here is just a normalization. Okay, it's there because you see that now if I sum over y, I sum all that over y, it gives me 1. So what I say is, it's probably not clear. What I suggest to you is to read a bit about the base formula. Okay, you have to first you need to understand properly the notion of conditional probability, and Google a bit about this Bayes law. We will not use it directly here. It's just something you should know. If we will use that later in the course on machine learning. I will spend much more time on describing what it is. Okay, but try to Google a bit about inference, statistical inference, and Bayes law. Okay, maybe the Wikipedia article.
I can recommend something.
Yes, I can recommend something, and we'll send you that. Okay?
No, if he wants to.
No, I can.
I can. Okay, I can too.
There is a YouTube channel called 3 Blue 1 Brown. Okay, I will write it in the chat. He made 2 or 3 videos about the Bayes theorem, and it's explained well.
Okay, that's great. Something, yes, you need to absorb with the words like this is a bit okay. You need to absorb it with. You know what? We will write it in the mail. You can send it to everyone, but I would like to see also. But don't worry if it's not there right now. It's not crucial right now. But my point was that the only thing I want to say about that is that even if it looks like a simple consequence of the definition of conditional probability, it's a very deep formula. And it's an extremely powerful formula in the context of inference. And inference is the way to understand something about some system using data about it. Here the y is interpreted as the data. The x are the unknown properties about the underlying system. And this formula tells you how to use this knowledge that you got from the data to infer something about the system that generated the data. Okay? This is a very deep and beautiful formula. All right, so this is all you need for the quality. It was much, much slower than what I thought. Maybe I can just, I will stop there. And next time what we'll do is, so if you look at my notes, what would be nice is that first you absorb a bit what we said today, and tomorrow I will quickly go through this chapter 2, which is just words about what is statistical mechanics and the notions that we are interested in. But you've already done that with Roman, phase transitions, emergence, okay, these kind of things. I will spend some time discussing that, and then I will introduce the notion of equilibrium. So you've already seen that, in the sense that system can be said to be at equilibrium if it is described by the Boltzmann distribution. In the canonical ensemble, it is described by the Boltzmann distribution, exponential minus beta h over z. Okay. And what I will do is I will just start, instead of getting from first principles from the derivation of the microcanonical ensemble, then you relax the constraint on the energy, you get the canonical ensemble, and you get this Boltzmann distribution. We will start by definition. I will consider models described by this distribution. I will give examples, Ising models and things like this. We will discuss that. And then, the day after, I will introduce the entropy in the sense of information theory. And we will derive the Gibbs-Boltzmann distribution. We will see why it is the proper form, why it is the proper distribution to describe complex systems. Okay? All right, so this is essentially it. So chapter 1, chapter 2, and I will do also tomorrow the beginning part of chapter 3. The chapter 2 will be quite fast. Maybe it will take an hour, and then I will spend an hour on the lattice gas and Ising model. Okay. Thank you. See you, the others, tomorrow.
Thank you. Bye-bye.
Ciao.
Bye.
Tac.
Also, it's too cold.